Welcome back to lecture 24. So in the last class I was talking about the QAM structure. So the first step was of course the map design, the constellation map design. So that I was discussing that how you can get it directly from the bit stream. Next step is obviously the baseband modulation. So this will be similar to the PAM. Modulation, demodulation. So we have the complex signal points. I am writing it as small, you know why, because although they are random, but this is basically what has been coming out. So this is basically one of the sample sequences. This is complex, and we have our filter, modulation filter P in the baseband. So we get our xt to be the waveform t minus kt for all k, all integers. Okay. And we have our nomenclature, which is WB 1 by 2t to be our nominal bandwidth, and the actual bandwidth is a little bigger than the nominal bandwidth. So this is the actual design bandwidth. So this has been discussed in that Nyquist criteria, right? So what we will do? So we will so this signal whenever is received, and assuming that the channel does not introduce any like noise, so you have, so this side is PT, which is giving you the signal xt, and this is the bit stream which was coming. Next is you follow by a matched filter qt, and then you are doing the sampling. So this is the matched filter. So the analysis is same, but only change is now that your PT can be in general can be complex and your xk is complex, but that does not matter, because when you are finally getting RT, that RT is basically x tau q t minus tau d tau, and which I can write as summation xk. So whether x is complex or real, it is irrelevant as long as we are having our g ideal Nyquist. So g t minus kt, in this way we can write. So this RT will be equal to RKT, I can say RKT will be equal to xk if and only if this GT is ideal Nyquist. So the theorem for QAM modulation for the matched filter is exactly the same as the PM. So I am not repeating that. Then we are straight away going to the I can state the final result, that our assumption is that our PF, which will take, that will be equal to root over of GF, and in general like this PF is complex. Then we know that this sequence P t minus kt for all k generates a like orthonormal basis function, set of orthonormal basis functions. Okay, so from here, once I have this signal, so I want to have the passband representation now, because that is where things are becoming interesting in QAM. So passband of QAM. Okay. So we are going by the DSP approach. Okay. So only assumption is that what we have to take, that in the baseband, suppose this is the nominal bandwidth, which is BB, and sorry, not the nominal, the actual bandwidth. So I have to ensure that when I am transmitting it, when I am modulating it, there should not be any overlap between the translated form and the baseband form, such that like there should not be any overlap with this. Then the condition is basically FC has to be greater than this BB. To BB basically, yeah, because this is also BB, this is FC minus BB. So FC minus BB has to be greater than BB. So FC has to be greater than 2 BB. So as long as this condition is satisfied, we can ensure that we can recover the signal entirely, and we have to ensure that these two don't overlap. Okay. Then our signal will be, the DSB signal will be in the same way. So the positive form will be xt, which is having only the positive frequency, e to the power 2 pi IFC t, and this is the analytic form actually. So the real signal is essentially the you have to add the complex conjugate with this. So you can take the complex conjugate. So that can be written as in this way as well, 2 to the power 2 pi IFC t plus x complex conjugate t e to the power minus 2 pi IFC t, which can be written as 2 real of xt cos 2 pi fct minus 2 imaginary xt sin 2 pi fct. So in the from the very first expression, if we think of implementing it, the implementation may not be very obvious, because the implementation will be as follows. So you have xt, what you are doing basically, you are multiplying with e to the power 2 pi fct, and then you are taking the real part of that, so 2 real basically. So this entire thing you can see the modulating filter, okay, so which will give you the yt. Now from yt, if you want to get back xt, what you have to do, you have to first transfer yt to y plus t. So somehow you have to get y plus t. So if you get y plus t, the next will be simply modulating back e to the power minus 2 pi fct, and you will get xt back. So what can give you the analytic waveform x plus t from y plus t from yt? This you have seen already. This is the so-called Hilbert filter or a Hilbert transformer. So the Hilbert filter can be it can be designed as follows. So HF, the frequency domain design, is basically 1 for all positive frequency and 0 for all negative frequency. Okay. However, we can make it even specific, because this HF is not L2. So to make it L2, what we can do, we can make it 1 only in the corresponding passband. So if we design something like HF is equal to 1 when f is between fc minus bb, fc plus bb, and 0 otherwise, that is good enough. So this will work. But in reality, we will not take this approach, which is the regular analog communication approach. Rather, we will take this equation. So the second equation, which is with the real part of x and imaginary part of x, and multiplying with the sine and cosine, this will be useful, because we know in the last class we have shown you that the constellation map can generate the real part of x and imaginary part of x separately at the very beginning. So we do not have to basically combine them, keep them separate, and that will work. So let us try the implementation. So that's the implementation of QA passband. The problem is if PT is complex, but as we discussed that even if P hat F is complex, we can get PT is real. So we choose some PT which is real, and that will generate the PT minus KT to be orthonormal as long as your QT equal to PT. So if this is true, so both can be real, but this will ensure that Q hat F conjugate is equal to P hat F. So this will be satisfied, so that will ensure your Nyquist criteria, isn't it? So least square is equal to GF, which is real, non-negative and symmetric. So I can get some PT real. If PT is real, then life is a little easy. Then your XT, so real XT can be written as, because real X, then the thing is separated. I will take only the real part of the constellation map because P is real already. So this will be real of XK PT minus KT is for all K. Similarly, imaginary of XT will be imaginary of XK PT minus KT. This is for all integer K. So then I can combine them. So what I can do, so I have already drawn the multiplexer. I am not these are already there already. So these are the selection bits, which are say U3, U2, U1, U0, and these are the values of the PAMs. I'm drawing only 4, but it can be anything. It can be like root m number of stages, or b by 2 bits. So here are b by 2 bits, here are root m number of stages, b by 2 bits. This is coming to be real of xk. This is coming to be the imaginary of xk. So what you are doing, you are basically first combining to make the sequence. So I can write it here. Sequence is like this: delta t minus kt for all k. Here also first make the sequence. Delta t minus kt for all k. Then you pass it through the channel, through the filter PT. So you get this is basically real of x, and this is basically imaginary of x. Now what? Now I multiply the other page. So you multiply cosine with this and sine with this. So 2 cosine 2 pi fct multiply 2 sine 2 pi fct, and then add them but with a negative sign for the sign. This is plus, this is minus, and then it is your yt. So this particular thing is called the DSB QC modulation. So which the full form is basically double sideband quadrature carrier. Because we were using the quadrature carriers cosine 2 pi fct and sine 2 pi fct. But mind it again, so here is another confusion which like some students have sometimes I have seen. They equate this with the SSB design, but this is not SSB design. This is very much double sideband, DSB only. I am not like taking half of the bandwidth from the spectrum. So the spectrum of YT is very much double sideband. Is that FC? That minus FC. I am not taking half of that. Okay. So next, what I can do now, let us think about the demodulation. So demodulation means from the passband to back to baseband and then getting the other stuff. So demodulation, this is interesting because what I want to do, I want to basically multiply yt with these quadrature carriers cosine and sine, and let us see what happens. So yt cosine 2 pi fct. So what is that? So yt I have already written here. So let us write down. So 2 real xt cosine 2 pi fct minus 2 imaginary xt sine 2 pi fct. Multiply entire thing with cosine 2 pi fct. So that will give you like 2 real xt into cos square 2 pi fct. So 2 cos square is basically 1 plus cos 4. So 1 is basically, it gives you real of xt, the baseband signal, plus real of xt, the baseband signal multiplied with cos 4 pi fct, minus this one is imaginary of xt sine of 4 pi fct. So this is one part. Second part is yt multiply with sine 2 pi fct. So in this equation, if you do low pass filtering, this and this will cancel out. Only the baseband will remain. So what kind of low pass filtering you have to do? This is 0, this is BB minus BB. You just perform some low pass filtering here. That will work because your FC is far away. So 4 pi fct, that is far away. Both sine and cosine both will cancel out if you perform low pass filtering. So you will get real over there. For the imaginary, I will multiply with the sine 2 pi fct. So I need the quadrature carriers. So quadrature demodulation, I can say. So again 2 real xt cos 2 pi fct minus 2 imaginary xt. Okay, I can multiply with minus 2 pi fct. So that will not, with the minus sign, sine 2 pi fct, sorry, sine 2 pi fct, sine 2 pi fct. So it will become, the first term is minus real xt sine 4 pi fct, again high frequency component. Next is plus 2 imaginary, so plus imaginary xt, so plus 2 sine square, which is basically 1 minus cos 2. So 1 minus cos 4 pi fct. So clearly from here the imaginary baseband signal comes out. everything else is high pass, like pass band. Minus imaginary xt cos 4 pi fct. So if I do low pass filtering, it will work. After that, what you have to do, because if your PT is so what is real xt? Real xt we have already written. So the drawing will be like this. So you have yt. So yt you have to like multiply with the quadratures cos 2 pi fct and minus sine 2 pi fct. That will give you the real of xt and imaginary of xt. And from there, what you have to do, you have to basically take out. So real of xt is what? Real of xt is real of xk into p t minus k. What did I write? Okay, in the last. So this is nothing but real of xk into p t minus kt. So after getting this, so this is nothing but some real number multiplied with the real pulse. So I can do matched filtering after that, which will give me this value. This is also real number with a real pulse. So do matched filtering to get these values. So that will work. So now before that I have to do low pass filtering. So think about this. So this is low pass filtering, and low pass filtering will give me this, and then I will apply the match filter. So this is qt followed by a filter followed by a sampler. This is qt followed by a sampler, and this will be my real of xk, and this is my imaginary of xk. So I am good. This is basically this will straight go to the constellation demodulation. Now what about this low pass filter? This low pass filter is some arbitrary low pass filter around the origin, around the baseband. Now what is this qt? Qt is also a similar low pass filter which works in the same baseband between minus B2 plus BB. So why do I need this low pass filter? I don't, because this matched filter will work only on the baseband signal. The other thing it will just kill. It will not take. It does not have any impact on these passband waveforms. So I can get rid of this low pass filter altogether. So this qt will simply work. Okay. So my final baseband final passband QAM demodulator design, it will not have this low pass filter anymore. Straight away qt will work. So I can design the demodulator straight away like this: yt multiply with cosine multiply with minus sign, and then you pass through the matched filter qt, do sampling at kt, and get the real of xk. This is imaginary of xk. And now from there you have to basically do the decoding. You have to basically get back the bit stream. So it is a simple task, not that difficult. We can talk about the degrees of freedom now of this PAM and QAM. So in PAM we know that the signal is coming at one symbol per t time. Okay. So if you take a long enough time duration, suppose you take a time duration of t0, which is very high. So how many symbols you can send through this time window? t0 by t symbols, which is equivalent to saying b t0 by t bits. That is what you are sending. Okay. Now, what is the relationship of B and T? So we know that the time period T is equal to B by R. So B by T is basically R. R is the bit rate of the bit stream which is coming. So R is equal to B by T. So this is basically RT0. So many bits you are getting in T0, isn't it? Now let us look at this from the degrees of freedom of the baseband waveform point of view. So we know that the baseband waveform, what is the actual bandwidth? The actual bandwidth is a little greater than WB, which is the nominal bandwidth. Little greater than. So it is basically having parameterized with respect to that alpha, right? When we designed the raised cosine filter. But we can take arbitrarily close to this WB. If so, if that is the bandwidth and our total time is T0. So what is the dimension of that signal? We know dimension is equal to degrees of freedom, right? So the dimensionality theorem, our Fox theorem, it says that the dimension of such waveform is 2 BB T0, and if BB is close to WB, then that is approximately equal to 2 WB T0, isn't it? So what is that? So that is the total degrees of freedom. This is the total dimension. So which is equal to WB is 2 WB is 1 by T, so T0 by T, that is the dimension. And you see that exactly matches with our intuitive idea of symbols, how many symbols you can set. So you are basically sending like one symbol per dimension. That is the understanding. It is one dimensional signaling, isn't it? For QAM, it should be the same. So in QAM, your bandwidth is 1 by T, it is double of this. But over there you have the complex signal, so you can send 2 signals per dimension. So your dimension is half of this, so W into T0. So but over there you have the complex symbol, your constellation map is complex, so you get the same kind of waveform. So even with this simple technique of PAM or QAM, what you are achieving, you are basically achieving the limit of degrees of freedom. So the total degrees of freedom which is possible is T0 by T, and you are achieving exactly that. So this is spectacular. So if your bandwidth loss is very less, if your alpha factor in that filter design is very small, then you can actually come very close to the possible of symbol, and you can clearly see that if this is large, then this particular value will be large, this 2B BBT0 will be a little larger, and you can send this amount of symbols. So your efficiency basically depends on that alpha. So alpha of that filter design. You can see how things are connected. So how much spillover in that spectrum you are having in that low pass filter PT design, that is exactly what is the efficiency, lack of efficiency in terms of the signal bit carrying capacity of the capability of this modulation method. Okay, so far so good. These are all good things. Now one thing is implicit in this entire process of modulation and demodulation, especially demodulation, which I did not talk much, is the following. How do you know what is cos 2 pi FCT? Because in the modulator side, when I discussed modulation, I discussed that there is some there is some 2 pi, this is the modulation transmitter side, 2 pi FCT. In the demodulator side, I am also using 2 pi FCT. This is one thing. Secondly, I am using a sampler which is working on KT. how do I know that this is having identical phase as this, even if the frequency is same? Even if you know the exact frequency, how do you know that they are having the same phase? And then how do you know what is the sampling time? So these are critical issues. What happens to the constellation if the phase here is not exact? Let me tell you. So what is our demodulation equation? Yeah, quadrature demodulation equation. So suppose this is not 2 pi fct. Let me write down fresh. So suppose like phase error in demodulation. So yt, suppose this is cos 2 pi fct plus phi. Okay. So what will I get? I am not writing the entire thing. I am writing only the baseband. So baseband will be, so cos 2 pi fct plus phi. So you will have a cos phi left over here. So cos phi, if you put inside, it will be e to the power j I phi. So it will be, so if you pass it through the matched filter, suppose your KT is perfect, KT works fine. This is low pass filter, so fine. So this will be real of xt e to the power I phi. Similarly, after low pass filtering, similarly yt sin 2 pi fct plus phi will be equal to imaginary of xt, that's minus, and LPF e to the power I phi. So what is e to the power I phi? E to the power I phi is counterclockwise rotation of phi on the unit circle, like around the origin. So e to the power I phi is basically like counterclockwise rotation around the origin. So what will happen to the constellation if this happens? Suppose phi is say pi by 8. Okay, and you are working on a PSK system, suppose. So your constellations were, this was your A0 and this was your A1, which is having angle pi by 8 from here. This is say A2 at pi by 4, A3 here, and so on, A4 here. Now what is happening, for every symbol which is detected, you are getting a pi by 8 phase shift. So A0, if A0 has been sent, it is received as A1. If A1 has been sent, it is received at A2. If A2 has been sent, you are receiving it as A3, and so on and so forth. So everything is ruined. Even if it is not pi by 8, even if it is small, it can mess it up. So this is for a PSK scheme. Suppose you have a regular QAM scheme where you are having the constellation like this. So what will happen if you introduce phase error in this passband to baseband demodulation in the DSB scheme? Everything will rotate. So it will rotate, all values will rotate according to this pi by 8 or whatever value. Everything will rotate, and the constellation whatever we are receiving, it will not resemble to anything which has been sent. So this is problematic. We have to know what is the phase. This phase has to be known correctly. Second thing is the sampler. Of course, unless you can sample it properly, you are not going to get this. So the clock has to run in the perfect way, and these local oscillators, they have to run in the perfect way. So this entire business of timing recovery or synchronization, this is a enormous task. So I can talk timing or phase and clock recovery. Also frequency. So frequency of the FC, phase and clock recovery at the receiver. And you can say this to be synchronization. So this is a huge task, which is the problem for analog communication also, but here you can clearly see what the problem is happening. So even if we don't assume there is any noise, even without noise, this is becoming mess. So this will be a big issue, and we will discuss this during estimation. So estimation will come a little late because we have our detection and capacity, those things are immediate. We will do that first. But please appreciate the problem here, that we are assuming that everything is available to us, and so we have done modulation, demodulation, etc. That is not so easy if you do not have the synchronization properly. In our analog digital communication laboratory, things are easy because the same oscillator you are using for modulation and demodulation, so there should not be any problem. But in reality, that is not the case. So we'll talk about that estimation later. But for the time being, we'll stop. We'll think that okay, fine, our modulation is over. Now we will go to the detection. The detection problem is when detection will problem will arise. So let me motivate that properly. So if a channel has no noise, our job is already done. We don't have to do anything else. So we got back the signal, and that signal will straight away give the symbol, and those symbols will straight away give the bit stream. So our communication is complete. However, things are not so easy. So channel will give different kind of issues, but mostly all the issues are decoupled from each other. So for example, the attenuation or phase distortion, those issues are mostly separable from the noise issue. So those things I am not touching at all. Distortion I am expecting you have already done in analog communication. So I really cannot go there. That will take huge amount of time. But that is fundamental in both analog and digital communication, and you have to do some equalization for that, right? To have like nice unit amplitude and linear phase response kind of filter. To have the channel behaving like that, you need equalization. So that thing is understood. The problem which will be more bothered here in digital communication is that of noise. So we know that our signal YT is the passband signal, and I am talking about the real channel. So real channel is a noisy channel, and the kind of noise which will be there can be different types of noise, but we are bothered about mostly with this noise, which is additive white Gaussian noise. So this channel will inject some additive white Gaussian noise to this. So your signal will be at the receiver side will be YT plus NT, and then it will go through the passband to baseband transition, then it will go to the modulation part, demodulation part and decoding part. So this is the real channel. However, we will show you that we can get the abstraction to a baseband channel also, equivalent baseband channel also, over where if this is additive white Gaussian noise, the power spectral density is like flat over the entire frequency band, then even in the baseband equivalent channel, it will be same additive white Gaussian noise with the same power spectral density, so there should not be any issue. And we can take the equivalent baseband approach over there, forgetting the true modulation, the baseband to passband and passband to back modulation, and we can work in that equivalent baseband channel, and we can assume that to be the same additive white Gaussian noise with the same power spectral density. However, if it is not white, if it is some other kind of noise, say pink or some other kind of coloring, then this thing will not work. We have to do the proper transformation, but that will be a little beyond our scope. So for this it will be same, it will have the same kind of behavior. Okay, now in this setup we have to basically do we have to take it to the discrete time level, because this is continuous time waveform, baseband waveform. So in the discrete time level, what will happen to this noise? So how to take this to the discrete time level? So we know the discrete time level xt has the following like orthogonal expansion, which is xk p t minus kt. This expansion, this Fourier expansion is there. So that will give you from this waveform, from this function, baseband function, we know how to convert it to a sequence. What will happen to the noise? Does noise also have some orthogonal expansion? Does the noise function also have some orthogonal expansion? So this will be our topic in the next class. In the next few classes, it will take probably three classes, and after that we can actually go to the detection problem, because without that detection will be difficult. So once that noise comes into picture, once we can write, if possible, suppose if possible, that this xt, which is having this orthogonal expansion. So if my nt also does have some orthogonal expansion like this, some nk p t minus kt with the same basis function, then I can write this output, which is say x tilde t or something like that, which is corrupted basically. We can write that as like we can perform the masked filtering on that, and we will get the output to be xk plus nk. So if I get the output to be xk plus nk, then I can think of that in the constellation that nk will be a complex number basically, right? So whatever be the xk, this was the true value, and nk is corrupting it. So it is shifting it to any direction, because this is also a complex random variable. So that will create problem, because without the noise we know that the number of possible symbols is m, is equal to 2 to the power b. That is the total number of possible symbols in the constellation. But whenever this n arrives, this n is a continuous random variable. So that makes the possible number of outputs, the symbol outputs, to be uncountably infinite, because this is having uncountably infinite numbers. So your detection is another like approach which will do a quantization kind of stuff, but taking into account the statistics of this noise. So it will try to find out that what could have been the original xk if noise is not present. Okay, so we'll talk about detection theory, but before that we have to understand that how we can expand noise. So we have introduced already the noise to you in our random process discussion, and you know Wiener-Khinchin theorem, but one thing which I left that time is the orthogonal expansion. So we'll talk about that, and this theory is basically the Carr-Huhn and Loewe expansion theory, which will be our topic of the next class. So before that you have your exam, so do it well. Your exam is up to lecture 20, and then let us see that in the weekend if I can make a few lectures on this Carr-Huhn and Loewe expansion and this posing the problem for detection. Okay, so we are at a good position. So right now how we are approaching the rest of the semester, it will be as follows. I can write here only. So the next topic will be noise expansion, scale expansion basically, and we'll work for, say, identified Gaussian noise and Brownian motion. Then we'll go to the detection theory. We'll not go to very deep, too much depth. It will take around 3-4 lectures possibly. So the total lectures will be 6 around. Then we'll talk about capacity, of course, and we'll talk a little bit about channel coding. These things will come together. So these two will come together, these two will come together, and finally we'll talk a little bit about estimation. Estimation is basically the synchronization. So what I discussed just a little while ago, that how to get the clock and phase, the PLL, phase lock loop, those things. So let us see. This will be around 6 lectures. This will be around 6 lectures. This will be around 3 lectures. 6 to 7 lectures, say. So around 16 lectures are left. This is 24th. So 24 plus 16 is 40, as I promised. And the previous 8, so 40 plus 8, 48. So with 48 lectures, I will conclude. There will be no wireless communication or fading in this course. Okay. So all the best. And your final exam will be on the entire 40 lectures. So please be fast. Now read it all. I have given you enough time to follow it. If you have followed it, the rest of the lectures will be cakewalk. It will be really, really easy. Okay. All the best.